Let's talk about the minor losses. So most pipe system, however, consists of considerably more than strict pipes. These additional components like pulp, valves, bands, and teeth, and other add to the overall health loss of the system. Okay, like what I said before, we have major and minor losses. So this is some components of pipe system that are related with minor losses, pipe entrance, sudden expansions, sudden contractions, pipe exit, elbow, whether it is a 90 degree, 45 degree, 30 degree, or 60 degree, and also valve, T, and other. What we need to do is we need to know actually the coefficients of the minor losses, which is what we call it as K. The minor losses coefficients, or K, for an entrance loss, we find K depend on the R divided by the R is, you can see from this figure, at the entrance. Okay, and D is the diameter of the of the pipe. You can see here the higher the R per D ratio, RB ratio, the smaller the coefficients of minor losses. This is for sudden expansion loss. For example, if you have the piping system like this is a small pipe, and this is the bigger pipe. We can also calculate the based on the ratio of A1, which is the area of the smaller pipe divided by the A2, which is the bigger one. Okay. Also, if we talk about sudden construction loss like this, bigger one then becomes smaller one. You can also use this diagram. Or maybe we have diffusive loss, something like this. What we need to do, to know the decrease of the bigger pipe like this, and then we use these equations. We use this graph to find these equations, and then we solve the problem. We solve this equation, we will have the minor losses coefficients. Also, if you talk about elbow, these equations that we can use, or this diagram we can use to find the KL, or minor loss coefficients, but also we can use this table. For example, if we use elbows with regular flanks 90 degrees, we will have, or we will get 0.3 KL. Okay, like this picture. Or if we have a return bands like this, okay, if it is flanked, we will have 0.2, 0.2. If it is threaded, we will have 1.5. And other thing like fobs and teeth like this. So use this table will give us the minor losses coefficients. So This is an example of piping system. We want to flow the fluid from this position into this positions. Okay, this is the piping system, and we use pump since the positions of this first tank is lower than the positions of the second tank. Okay, what we need to analyze in here, of course, we need to calculate the head loss. Like what I said, before, we have major losses and minor losses, right? Yeah, like this. So if we put all the equations into total head loss, we will have these equations. This is for major losses, and this is the coefficients of minor losses. Why we have 6? We can see from this picture. First, we have shaft entrance here, so we have K1. We also have FOB, so this will be K2. We have here elbow, this will be K3. We have also another elbow here, regular screwed elbow, this will be K4. And we have another FOB, which is K5, and the last one sharp exit as a K6. That's why we have K1, K2, K3, K4, K5, and K6. And other than that, we also have these major losses since we use pipe. So of course we have friction here, here, and also in here. Okay, and then if we put this whole thing into the equations, because we have pump here, right? So our equation will be like this. In the previous section, I have explained that if we don't use pumped, we only have these equations until this. Okay, but since we also use pumped, so we'll have HP, which is head of pump. So normally what we need to calculate, actually it is the head of the pump. So if other head is bigger, we need also to increase the head of the pump. I will show you in the next example how to calculate the head of the pump. This is an example of calculating the pump power of this system. So actually it is the similar system with the previous case, but I will put it into the context. We will have the water with density 998 with also the viscosity 0.001, pump between two reservoirs at 0.0056 meter cubic per second is the flow, and 120 meter of the pipe and 5 centimeter diameter of the pipe. So what we need to do is we need to compute the pump power required. This is the table of all the minor losses coefficients. So since we have 6 minor losses coefficients, we can find it or we can calculate it based on this table. Okay. For example, sharp entrance in here, the minor losses coefficients will be 0.5. Of course, you can find it based on the table or the figure or the diagram that we have learned in the previous sections. Okay, and for example, for sharp exit, sorry, we have the K or the minor losses coefficient as 1. Okay, based on the system, then we need to calculate based on Bernoulli equations. So this is the solutions of our problem in a previous example. We use Bernoulli equations to solve our problems, and based on the case that we have reviewed in the previous slides, we know that the the pressure 1 and the pressure 2 is equal, so it is atmospheric pressure, and also the velocity v1 or v2 is equal to 0. So that's why we cross all the things related with this. We cross this one, we cross this second, or we delete this one and this one, and we will have these equations Z1, Z2, HF, HM, and HP. And if we try to calculate the HP or the pump head, we will have these equations. Okay. So what we need to do next, of course, we need to, since we have this from the our case, which is the elevations of the second positions of our reservoir and the elevations of the first reservoir. We have this from our case, but we need to calculate the major losses and the minor losses. First, let's calculate the major losses. What we need to do, we need to calculate the Reynolds number first. Since we don't have the velocity from our case, we need to calculate the velocity first based on these equations, since it is the mass flow or the discharge, and this is the area of our pipe. Then we have that the velocity 2.85 meter per second. And then we use this into these equations. We will get that the Reynolds number is equal to 1.5, 1.4. Okay, it's actually 140 thousandths. Okay, this is the Reynolds number. And then with Moody diagram or Kohlberg formula or Holland formula, we find that the friction factor is equal to 0.0 second. Okay, this is for for major losses. For minor losses, we can calculate it based on the table that we had in the previous slide or previous sections. Okay, and for the total, we have 12.2 as a minor losses coefficients. Then the next step, we calculate the head of the pump. We put all the things that we knew into these equations. So the elevations of the second reservoir is 36 meter, and the elevations of the first reservoir is 6 meter, and this is the velocity of the flow, this is the density, and then we have major losses and minor losses coefficient here. And then we find that the the head of the pump is equal to 55 meter. Then we can calculate the pump power based on these equations, where pump power is equal to Rho, G, Q, and HP. Rho is the density of the water. It is gravitational accelerations. It is discharge of the flow, and it is the the head of the pump. And then we have that the pump power is equal to 3 kilowatt. What we need to know from this problem and solutions, that In this case, as an engineer, you need to install the pump with the specifications 3 kilowatt or higher than 3 kilowatt. You are not allowed to install under 3 kilowatt pumps, because if you install the pump with under 3 kilowatt power, your pump will not working properly. Maybe it's not working at all. So that's why what you need to do, install higher or at least similar with or same with a 3 kilowatt pump. Okay, that's the thing as an engineer that you need to do. Finally, that's everything from our last module. In this case, when we talk about uh, pipe flow system, I think we have already discussed about the major losses, minor losses, and about the fluid development, entrance regions, laminar, uh, transitional, and also turbulent flow. So we have covered everything in this model, and I hope this will be something that very beneficial for you as an engineer students, and you can use this material in the next chapter of your life as a professional mechanical engineer. That's everything that I need to tell you in this course. Thank you very much. Terima kasih.